The first thing I would like to maybe come back a bit to this definition of the Markov decision processes that I gave last time, just because it was maybe a lot of information at the same time, and just come back to well understand these different interpretation with these disturbances of space for some model, which is a conception problem. So I recall you what is a conception problem. Is a conception problem. Okay, let us start with some description with the disturbances space. So in this disturbances space, okay, maybe you can write it down. Yeah. So conception problem. So how you can describe the problem is that, so at each time n, you have some capital, which is xn. It is your capital. Okay, and then you will have some new capital at time n plus 1, which will be xn plus 1. So what will be the evolution to go from the capital xn? So xn, of course, belongs to 0 plus infinity. And what you are, the action that you are doing on this capital is that you can extract, when you have xn here, you extract some quantity from this capital that you will use for consumption. And this quantity depends on the capital that you have. And of course, it will be less than xn. You cannot extract more than what you have in order to consume it. So it is your action. The action is there. And then what is the capital that you will have when you will extract? You will have xn minus fn of xn, of course. Okay, it is the money which remains in the bank, if you wish. And then because this money is in the bank, you can have some, or you invest it in some on the financial market. Then it will evolve according to some randomness. It will become higher or lower depending on the state of the market. So to analyze with them, we say that xn minus fn of xn will be multiplied by z n plus 1, where the zn, the zk are in R. Sorry, they are positive strictly positive, and IID random variable, and they represent the returns that you have when you invest this capital at time n. When you remove what you consume, then it will multiply by some random quantity, which represents the random rate, and you will get some new capital at time n plus 1, which is xn plus 1. So this is a model. So this is a model, and this is a Markov decision process, but it is not written exactly in the framework that I gave at the beginning. It is written in the framework of the disturbances because of this, the presence of this random variable. But if you wish, imagine that you start with a process which is defined like that, so which is quite natural. Okay, and of course, the evolution of this process depend on the action that you will perform at each time on this function fn. So in this context, what is the state, the space, the state space? So it is the space where is living xn. So it is what I denoted E usually. It is just 0 plus infinity. Now, what are the action space? So you see the action is represented by the capital that you are extracting for your consumption. So it is also something positive. So A, the action space will be similar, it will be 0 plus infinity. But now you have some restriction about the capital that you can extract. You can only extract some quantity which is less than xn. So it means that if x 0 plus infinity is so it is the state, the capital, the state of the capital, So dnx represents the actions that you can perform at time n when you are in the state x. When you have the capital X at time n, you can extract some quantity, but this quantity, which is a in the action, has to satisfy that a is less or equal to x. Okay, you cannot extract more than what you have in your state, in your capital. So it is the dnx, and we were denoting this dn was just it was just the union over x in e of x times dnx. So this is a subset of e times a. Okay, it is the complete set of all the action, but the most important subset in this conception problem is this dnx, which represents the actions which are allowed to perform when you are in the state x. Okay, and so now it is. Now I introduce also some other notation, which was the QZ, which was the kernel transition corresponding to this disturbance. It was called disturbance, this guy. And here, this a priori, this is the probability distribution of the random variable Zn plus 1 when at time n, so it depends on n in principle, when you are in the state x and in the performing the action A. And here you see it is just the law. It is the law of z n plus 1 when xn is equal to x and fn of xn or fn of x is equal to a. And in this conception problem, this z and the law of zn plus 1, since they are IID, this zn plus 1 is completely independent of xn. So in fact, the law of zn plus 1 is independent of x and a. It doesn't depend of what is the value of xn, what is the actions that you are performing. These disturbances here in this model, but in some more complicated model, we could assume that this q and z will depend on the x and on the a. Okay, so it will depend on, it is not necessary that it is independent of xn, nor independent of the action. But in this simple model, it is. And this is the kernel corresponding to the disturbance. But now, if this is the first vision of the, okay, so what I can precise something else, yes, it is with the notation that introduced. In this case, you have xn plus 1 is equal to zn plus 1 times the capital which is not consumed, time n. So xn minus fn of xn is the capital which is consumed. Xn minus fn of xn is the capital which is remaining in the bank. And because you have some return which is given by this zn plus 1, so here it is a new capital that you have at time n plus 1. And this one, in the notation, it is, we write it like it is a function of xn of fn of xn and of zn plus 1. And so you have some function Tn, which is depend on x, on the action, and on the z, which depend on time n, and which was called, so how do we call it? It was called the, let me come back to the course because I don't remember how I called it. I called it, oh yes, the transition kernel. So it is, this is a transition kernel you see here X is in E, A is the action is in A. More exactly, A can only be in Dn of X because it is the action is allowed to only in if you are in state X, you have only a certain number of actions that you can perform, not all. And phase Z is in phase set Z, phase calligraphic Z, means that it is in the space of disturbances, which here is equal to 0, 0, open, 0, or plus infinity. It depends on the support of the random variable Zn plus 1. And so now, if I interpret it as so phase xn plus 1, if phase xn, you see, xn, in phase example, if you look at phase definition here, so it is a Markov chain, which is time homogeneous, but the law of phase Markov chain depend on the strategy that you are following at each step. So if you change the Fn, you take some different strategies, then you will change the law of your Markov process. It will remain some Markov process, but with different laws. And so it means that here, Xn is a time homogeneous. Okay, I don't have to write it. Is a Markov chain, Markov process, more exactly. And E, but the law or the probability transition of his Markov process, but the law depend on the strategy which is followed. So the strategy is the data F0, F1, the action at time 0, action at time 1, until the action at time n minus 1. Because I recall you that I consider only finite horizon time Markov decision processes. So at time n, we stop the process. So it is a Markov process in here, but the law depends on the strategy, and you can see it very well, because if you want to evaluate, so it is the notation that I used, I say that I call it pi. Pi is a strategy. And if I look at what is the probability, so it depends on pi, on the strategy. So for each pi, you will have some new probability on the space of the path of your Markov process. And if you start initially with some capital, which is small x, then if you look at the probability that xn plus 1 is in B, B is a subset of R plus, given x0, x1, xn, so given the sigma field generated by x0, x1, xn. So if you look at the definition, which is here, okay, you see that in fact it is equal to the probability. It is equal to the probability that xn plus 1 belongs to B, given xn and given fn of xn. It doesn't depend on the past, depend only on the present state, xn. In fact, I could write it, sorry. Write it like just in xn, because fn of xn is just a deterministic function of xn, but this probability depends also on the disturbance, the n plus 1, which is here, okay? And in fact, so this guy is what we denoted. We denoted this probability. Okay, just 1 second. So we denoted this guy this probability, we denote it like Q n, so dependent term n, of B given xn and fn of xn. So this probability transition kernel is not the same as the one that I introduced before, which was the QNZ, which was the kernel distribution of the disturbances. Okay, it is not the same, but they are related. Because here, if you compute this probability transition, what you will observe by definition is the probability starting from x pi that Zn plus 1 times xn minus fn of xn belongs to B given xn. And Zn plus 1 is in fact independent of xn. So, but here you have some, it is independent of xn, okay? But here you have something would depend on xn. Okay, so if I want to compute, so if I want to see the connection between this guy and the Q and Z, so what I do is that I compute, so I want to compute the Qn B small x small a, what is this guy? It is the probability x pi of Zn plus 1. So xn minus fn of xn in B given xn equal to x, fn of xn is equal to a. Okay, so it is exactly the probability that Zn plus 1 times x minus a is in B. And now you see it is xn equal x, fn of xn is equal to a. But now since the Zn plus 1 is independent of xn, this is in fact just what I denoted before, the QZ, the probability distribution of Zn plus 1, which is where QZ of the set Z in R plus, that Z times X minus A is in B. Okay, QZ is a probability distribution of the random variable Zn plus 1, which is independent of Xn. And you see here, okay, the relationship between this kernel for the Markov distribution process, when you encapsulate it in the framework, the initial framework, and the relation with the QZ when you describe this Markov decision process in terms of the disturbances. So there are always these two kinds of description which are possible for any Markov decision process. So here it is explicit, and sometimes it is better to describe it with these disturbances interpretation, and sometimes it is not necessary to go through these disturbances interpretation, but there is always some way to do it. So just to recall you the notations that introduce this Zx minus a, it is the Tn, okay, here it doesn't depend on n, but it is a Tn of x, a, z. So I hope that I have been sufficiently precise now to show you, to come back to what I wrote last time in the general case. In the general case, you see, you can always, if you start from some Markov decision process, which is defined just in terms of this Qn, of this transition kernel for the X, then you have just, you can define some disturbances space and some fictive random variable Zn plus 1 and so on, just you have to take that the distribution of the random variable Zn plus 1 at time n. So the distribution of Zn plus 1, given that xn is equal to x and that fn of xn is equal to a, is just this qn of b given x and a, okay, which is written here. But so in the case of the conception problem, the probability distribution of the Zn plus 1 was completely independent on the xn and the fn of xn. But in some other circumstances, it can depend. If the distribution of Zn plus 1 can depend on xn or on the action, just of fn of xn. So it is a reason for which usually it is a kernel where there is a dependency in x and a here. And now, it is what we have seen previously with in the case of the consumption problem that I described with in terms of the disturbances, is that the relation between the kernel for the Markov chain xn, qnb xa, is related to the qnz by this relation. So it is a relation that I wrote, but in the case of the conception problem, I didn't have the dependent in x and a. So it was just this equation. It was not depending on x and a in the conception problem, but in some other problems can depend on x and a. So I hope that now it is a little bit more clear, this connection between these disturbances and the vision of the Markov decision process and the usual Markov decision process without the disturbances. At the end, you have to imagine that what is the Markov decision process? It is just a Markov chain, but a Markov chain with probability transition probabilities, the transition probabilities of this Markov chain depend on the strategies that you choose. So it is a reason for which in the notation, I always write P, X, pi. Pi denotes the strategy. So each time that you are changing of the strategy, then you are changing the transition probabilities of your Markov process. Is it a little bit more clear now, or you have still some questions, something that you didn't understand? Because it's true that it's a lot of information going at the same time, but it is a way that Markov decision processes are defined. So the definition is a little bit long to digest. Is it clear, or do you have some questions?
Yep, it is okay.
It's okay.
I see what's going on. Yeah.
Okay. So okay, now let's spend some time on that. Okay. So now let me come back to this slide. So, or maybe I can write it again. So what is the goal? So now we have this Markov process, Markov decision process with state E, it is a state, action space A, dnx. So dnx is the A in A, such that AA, which are allowed at time n when the system is in X, in E. And so Rnxa, so it is a reward, which can be positive or negative, depending on the reward, and that you get at time n when you are an xn is equal to x, and fn of xn, which is the action that you are taking, is equal to a. Okay, if it's fn, not the strategy. The fn is some function which goes from x into dnx. It is the action that you are taking when you are in state x. And gnx is the final reward at time n. We don't depend on the action because at time n, everything is finished. n, and we do time n when xn is equal to x. So I recall you that you have all these rules, decision rules that you have to take at any time n, and pi is just a strategy, is a data which is given by these n-1 decisions. So here all this function goes from x to e into gnx, which is a subset of a. We have to assume that they are measurable in order to have some well-defined strategy, because E and A are not necessarily finite space. It can be infinite. So we have to be a bit careful about some measurability conditions. So it is a strategy here. And what is the goal? Now, the goal is the following. So we define V0 pi of x is the expectation, the average of the total reward that you will get under the strategy pi. So you fix the strategy and you have sum from k equal 0 to n-1. So during this each stage, you have some reward given by the Rn. So it is Rk here of xk and fk of xk. So fk of xk is the decision that you are taking at time k when you stay your system in the state xk. And you have the final reward, gn of xn. Okay, and here why there is a x here, it is because you are starting from x. So you can write it like that or write it with some x here as you wish. This is the same. And the goal is to determine what is the best strategy in order to maximize this V0 pi x. Given x, we want to find what is the best strategy. What is the best strategy to get the maximal reward? And to do that, we'll say that we will introduce some algorithm which is based on the Bellman's equation. And for that, we need to introduce some intermediate rewards, which are defined like that. It is expectation by following the strategy pi of, instead of starting from 0 here, I will start from n. So it is some ingredient we will use in the proof. K, xk, fk of xk plus gn of xn, given that xn is equal to x. Okay, and here I could put what I want. I could start with any initial condition. It will not modify the value of this guy because of the Markov property. Given that at time n, I know that I am in x, I don't care about the position, the initial position I was starting from. It will have no influence. The important thing is that I am at time n, I am in x. So phase one, generalize phase V0, and it will play a role in the algorithm that we will define in a few minutes. Yeah, some time. Okay, so it is the goal. The goal is to find the best strategy. So let me come back here. So of course, what I said last time is that in order to, so we define this, I introduce this Vn pi x, which is here. And so the Vnx is just the supremum over all the strategy. Since the Vn pi depends only on the actions that you are taking from a time n, small n, n plus 1, n plus 2, until capital N, the strategy, the supremum, is taken over the strategy pi, which starts from small n and which goes until capital N minus 1. Okay? And so we called a policy or strategy optimal for the n stage if V0 pi x is equal to 0x. Okay, it is some strategy a priori it is not unique, which maximize the average benefit from your evolution of the system. So I introduced the expectation of his random variable, so you have to be sure that all his random variables are finite, and it is the reason for which there is this integrability condition, which is here. So before to come back to this integrability condition, let me recall you something, which is, so when is the expectation of a random variable well defined? So if X is a random variable, so with values in R, expectation X is well defined, okay, is well defined if X is positive or X negative by allowing the values plus infinity and minus infinity. Okay, for example, I don't know if X is yes, if X is a Cauchy distribution. If X, okay, has a law, as a density, say 1/2 pi 1 divided by 1 plus x squared, indicator of X positive. So it is not exactly Cauchy because I introduced this indicator function, but it's the reason for which I divide by 2. Okay, consider this random variable, which is a random variable which is positive, because here you have this indicator function. It is a random variable. So what is the expectation of X? Okay, the expectation of X is just interval from 0 to plus infinity, 1/2 pi, X divided by 1 plus x squared dx, which is of course not integrable function, so it is equal to plus infinity. But okay, it's not a problem. I can say that it is plus infinity. Similarly, if X is negative, and as density, for example, 1/2 pi, 1/1 plus x squared, indicator of X negative, I will get the same. I would get that Ex is equal from minus infinity to 0 of X, 1/2 pi, 1 plus x squared dx, and it's equal to minus infinity. So it's also well defined that it takes a value minus infinity. Now the problem is that if X does not have sign, definite sign, it can be positive or negative. So for example, if I take this one, X as density, just a Cauchy distribution, 1 plus x squared, respect to the Lebesgue measure, then we cannot define Ex. You cannot define it because it is, you see, you will decompose your integral here. So the formula would be integral over R, X, 1/pi, 1 divided 1 plus x squared dx. But then you can cut it from minus infinity to 0 plus integral from 0 to plus infinity. This one gives minus infinity. This one gives plus infinity. And what is minus infinity plus infinity? We don't know. However, if from generally what you can do is the following. You can take X and you write it into its positive part minus its negative part. Okay, so X plus and X minus here. So it is some notation that I will use all the time. Is the maximum between X and 0. So it is a positive random variable. And X minus is the maximum between minus X and 0, which is also positive. And then expectations, since they are positive, expectation of X plus in 0 plus infinity makes sense, is well defined, and the expectation of X minus in 0 plus infinity makes sense. Okay, so the expectation of x plus and the expectation of x minus are well defined, but now the expectation of x can be well defined only. You can define it well defined as expectation of x plus minus expectation of x minus if and only if E of x plus is finite or expectation of x minus is finite. If both are infinite, it is impossible because it is plus infinity minus infinity. But if only one of them is infinite, it is not a problem. If this guy is, for example, 2 and this guy is plus infinity, then it will be minus infinity. Okay, so maybe it is something which is not so familiar for you, but I will say that expectation of x is well defined, so it is a choice. Okay, I could make some other choice, but well defined with values in minus infinity. See, minus infinity is allowed, plus infinity is not allowed if expectation of x plus is finite. I just need that the positive part of x is integrable. And then maybe the expectation of x minus will be plus infinity, and then in this case, I will get some expected value which is minus infinity, but it is not it's not a problem. If I allow the value minus infinity, I can do it. Okay, just to okay, it is not some difficult thing, but it is a reason for which in this assumption, this interval assumption, I just ask that the positive part of his random variable, this is a positive part of his random variable, which is written here, has to be finite, okay, not the absolute value. Of course, if you have the absolute value of his random variable, which is finite, then it implies that this positive part is finite, but we can require less, just a positive part. And if you have this condition, which is satisfied, so it is a supremum over all the strategies and the supremum over all the initial points, then all the elements that I define here make sense. Maybe with the value minus infinity here, maybe it belongs, this one belongs to minus infinity included plus infinity excluded. Okay, and this one is a supremum of something which is also well defined. Okay, maybe it will be minus infinity and maybe it will be plus infinity. It's well defined in minus infinity plus infinity, both included, because maybe it's a supremum over Vn pi x. Vn pi x. No, sorry, this one is excluded. Okay. Because of his interoperability condition. Okay, so now it was just to say why everything is well defined. Now we can pass, if you don't have questions, to the algorithm to compute the best strategy. Is it okay, or we have some question? No, it's okay. So, okay. So the main, so the algorithm to find the best strategy is based on this what is called the Bellman equation, which is written here. Wait, that. Okay. So the Bellman equation is written here. So, and we will develop here. We will prove that this is the main point to find the best strategy. Okay, I need to introduce some notation before to make the proof. So you remember that my Markov decision process is defined through this kernel Qn, which represent the probability distribution of xn plus 1 when the states, the system is at site x at time n, and when the action at time n performed is A. So it is the physics, you can write it, you can see it like the expected value, this guy of V is a function from E when given that xn is equal to x and fn of xn is equal to A. So, and I assume that we have some function V who said that this interval is finite, okay, for any n. And for any xa, which are in the allowed set of decision rules. So now I introduce some three operators, this ln, this dnf, and this tn, which is called the maximal reward operator, and we'll see in the proof why these operators appear naturally. So maybe if I do the proof, maybe it will be simpler to see why these ingredients are natural. Just 1 second. So yeah, it's better to start the proof, and we'll see why we have to introduce these different operators. So let's just start the proof. The Bellman of the Bellman equation. So we have this Vnx is equal, by definition, Vn pi x. So when you follow the strategy pi, it is the expectation of the sum from k equals small n to capital N minus 1 of f rk xk fk of xk, so reward at time k, plus the final reward gn of xn, given that you at time n you are at site x. So, and the first thing that we will do is that what we want to do is that we want to compute the supreme over pi. So typical pi here for Vn pi x, it is a strategy. So here I should write pi here. Pi here is just strategy. We start as small n, fn, fn plus 1, f capital N minus 1. Okay, because here in the sum you start from k equal to n. So it is what you did before is not so important. At the end, we know that at time n you are inside x. So it is a strategy after the time n which is important. And this guy, it is V pi x, Vx, sorry, Vnx, okay, takes the supreme over all the strategy. So we want to compute these values, and what is the most important is to compute V0 of x, which is the total reward that you will get during your end stage evolution of your system. So there is, if you look at Vn pi x, so Vn pi x, it means that you're conditioned by the fact that in the final state is x, and since you are in the final state, you can not, the game is over, so you can just take the reward, the final reward, but you don't have any actions to perform. So it is just the expectation pi, but in fact would be completely independent of pi. You don't have any strategy to perform now, it is the final time, even xn is equal to x. And of course, it is equal just to gnx. and it is independent of pi, okay, because you don't have any action. So you can see it directly because here you see the sum starts at k called small n, but see if you take small n is equal to n, capital N, then the sum is the sum which is here is empty. And the same here, in fact, it doesn't depend on the strategy, because here the strategy, you can perform actions between the time small n and the time capital N minus 1. So at time capital N, you can perform any action. So it means that since you have that the supremum over pi, which is of Vn don't have strategy to perform. So Vn of x is equal to Gn of x. So it is a starting point. And we will show that we can deduce the value Vn minus 1 of x. We will write some formula which involve V capital N of x. And afterwards, we will show that Vn minus 2 of x can be expressed as some function of V function of Vn minus 2 of x, and so on. And so it is a backward algorithm in order to deduce at the end V0 of x. So it will be backward algorithm. So let me show now how we do. So yeah. So my goal now is to connect Vn pi with Vn plus 1 pi. So I fix first the strategy. And so the big strategy, so it means that here pi is the strategy between the time small n and capital N, like here, okay? And here the strategy, okay, is in fact the restriction, because it is the strategy between n plus 1 and capital N. So this pi that I did not with the same letter is a restriction of the strategy to this time interval, which is a bit shorter. Okay, but I will denote with the same letter. So let us try to connect first this Vn pi with Vn plus 1 pi, and later we will connect this Vn with this Vn plus 1. And then it will permit to have some algorithm to compute. So what is Vn pi of x? Vn pi of x is pi. Okay, here's the starting point, as I told you, is not very important, of the sum from k equal n to n minus of rk xk fk of xk plus gn of xn, given that xn is equal to x. Okay, this is a conditional expectation, and again, as usual, you have to isolate what depends on this event and what is not depending on this event. So it's the reason for which in this sum, I will start to split the sum in two parts. One part for k equal to small n, and the other part. So let us do it. So it is for k, okay, if k is equal to n, I get Rn xn fn of xn, given xn is equal to x, plus e pi dot sum from k equal n plus 1 to capital N minus 1, Rk xk fk of xk plus gn of xn, given xn is equal to x. Okay, so now the first term here is very simple to analyze, because x given xn equal to x, you just get some deterministic function. So this the first term is just equal to Rn of x fn x. Now there is a second term. So the second term is a bit similar to the Vn plus 1 pi, but in the Vn plus 1 pi, here I should not have n, I should have xn plus 1. So the idea is that to use Markov property, because as you see, this guy is some, it is some function of the trajectory after the time n plus 1. So we start at time xn equal to x. So we will jump with some Markov kernel to some new state at time n plus 1. And from this state at time n plus 1, then we will start with some new value. So if you use this Markov property, I recall you that we have that the distribution at time n, I recall you that the probability, if you have I, which is fixed, that xn plus 1 is in B, given that xn is equal to x, it is just q n b x fn x. It depends on xn by the actions that you have performed. Okay, so it's the reason for which here, if I want to fizz xn plus 1, so I can get the probability distribution of xn plus 1, given that I have xn equal to x. So it is expectation pi k, it will be the integral on e of the k equal n plus 1 n minus 1 r k xk fk xk plus gn of xn given xn plus 1 equal to y, close here. So multiply, I have to integrate according to xn plus 1 equal to y, given that xn equal to x. Oh, if I want to write it with the usual notation, yeah. Okay, it is a probability kernel of my Markov chain. Okay, you have to put some pi here, depend on pi. It doesn't depend really on the initial point, but I can put it like that. Okay, it's just Markov property. But this kernel here, I know exactly what it is. This kernel, which is here, this probability distribution transition, is given by this kernel. So in fact, I can rewrite this integral like it is this guy at the end is Rn x fn x plus the integral over e. So now what you recognize here in this expectation, it is exactly Vn plus 1 pi of y. So it is Vn plus 1 pi of y Qn of dy given x and fn x. Okay, this comes from, so I replace just this probability kernel is given by this guy, in fact. Okay, here it is written in terms of B, some subset B. Here it is just as the law. The law with the small y. Okay, so we get this relation. We establish that Vn pi x is exactly equal to this quantity. Okay, and okay, so this is the first relation, and it is the reason for which this guy. Okay, it makes sense to introduce. It makes sense to introduce the following operator. If you have v is a function. Let's go from e into r. Then we will define some function LV of x and a, where x is in E, a is in A, the action space, as Rn, so Ln, sorry, Rn of xa plus integral formula E of V of y, Qn dy given x and a. Okay, the reason for which I introduced this operator, which will appear in the slide. Everything is clear up to here, or there are some problems? No? It's okay? Yes, it's okay. Okay. So, okay, I see that it is time now to stop. So, okay. So the next step, or just before we will come back to that later, it is that we will have to take, now we will want to connect V and X. It is a supremum of a pi of the Vn pi X. Okay, so of course, this supremum of a pi, we will make some computation in order to connect it now to Vn plus 1, where it is a supremum of a pi. And but I don't have time to finish here with the proof, which is where we will have to introduce all these operator. But the first operator that we introduce, which is here, appears naturally when you try to connect Vn pi to Vn plus 1 pi. And then when we will try to connect Vn, so it is a supremum over pi of the Vn pi to Vn plus 1 pi, then this operator and this one will appear. Okay, but I will come back next week to the proof of his theorem and to get the algorithm to compute the optimal strategy. Now we don't have time to finish it; it's too long. Okay, so I don't know if you have some,
maybe
yes.
I don't want to like I mean, why we don't have time, because usually like the 1 hour is astronomically 1 hour 20 minutes, yes, because we started
Yes.
at 2, then we finished at 3:20, then we started at 3:20, and I suppose I think we are supposed to finish at 4:50.
Okay. So sorry, I was confused. Okay, no, you are right. You are right. So we have time. Okay, good. Thank you. Maybe I didn't. I was computing badly. Yes. Yes. Okay. Understand. Okay. So we can continue. So in this case, so perfect. So now we have to. We want to connect this V and X. We want to connect it to Vn plus 1 X, which is the same, but with a supremum over pi of Vn plus 1 pi of X. You see here in the previous computation, I was connecting this Vn pi X to not only to Vn plus 1 pi of X. In fact, it is to the whole function Vn plus 1 pi. If I want to compute this quantity here, it is not sufficient to know Vn plus 1 pi of x. It is necessary to know Vn plus 1 pi for all the y. Okay, but okay, here we will do the same. So let us start to prove some first some inequality, and then we will go to some to the equation. So Vnx is the supremum over pi, so I can write it. Here we have to be careful because here the supremum is all the strategy, okay? And the strategy, since it is Vn, they are Fn, Fn plus 1 until F capital N minus 1. While here, the pi is a strategy which is it is starting from n plus 1 until Fn minus 1. So I use the same letter, but we have to be careful that when we are talking about depending on the time, the strategy is shorter or longer. Okay, so I can write this supremum. It is a supremum over all the action at time n, n plus 1, n plus 2, n minus 1. So I can say that the supremum of the first action, Fn, so which belongs to, it is a notation introduced. I say Fn, I called it before a decision rule, and capital F index n is the set of decision rule at time n. Okay, and then you have the supremum over Fn plus 1, Fn minus 1 belonging to Fn plus 1 times capital Fn minus 1 of Vn pi x. But in view of the form of his guy, you see that the first term does not depend on the next action. So in fact, and so it means that you can write it. Let me see. Yes, okay, so let me write it a bit more carefully. So just to not be confused, here it is a strategy here, it is Fn plus 1 it is, sorry. The strategy here for Vn is F small n, Fn plus 1, F capital N minus 1, okay? Now, what we observe is that we have this formula which is written here, but I know that by definition of what is Vn plus 1, I know that for any strategy here, Vn plus 1 pi is smaller than Vn plus 1. Okay, because it is a supremum over all the strategy. The strategy are starting at n plus 1, but here also it is written like that, but you have to remember that here, in fact, this guy depends only on the strategy from time n plus 1 to time capital N minus 1. So in fact, I can bound it. I can say that this guy here is, because Qn, you integrate with respect to some probability transition. So if Vn plus 1 pi is smaller than Vn plus 1, then the integral of Vn plus 1 pi is smaller than the integral of Vn plus 1. So it is smaller than the supremum over Fn in Fn of the supremum over Fn plus 1 F capital N minus 1 of Rn x Fn x plus the integral over E of Vn plus 1 y Qn dy given x and Fnx. Okay, so for the moment it's just some inequality, and so okay, I can rewrite it is a supremum over Fn in Fn. The first guy doesn't depend on his Fn plus 1, Fn minus 1, depends only on Fn. So you can go outside of the soup. And in fact, the second guy, if you look, it's also now, since this guy is the supreme over all the strategy. So it is completely independent of the strategies which are here. So in fact, it is here. I can just write it like the integral over E of Vn plus 1 y Qn dy x Fn x. Okay, so it is a soup over Fn in Fn of this guy that was introduced before with the notation, this notation which is here. You see, it is in fact L n Vn plus 1 of x f x. Okay, and so it makes sense to introduce now a new operator, which is T n f v of x and of x for x in E and for f in dnx. Okay, see, because fnx is always in dnx. It is some action which is allowed when you are in the state x. So it is a supremum over all the a in dnx of ln v x a. So it is a second operator that I introduced, and if I introduce this operator, I can rewrite guy like T n Fn Vn plus 1 x x. So, okay. So it is this operator is the second one which appears in the slide. If you see, it is this one, this TNFV. It is a function now. Before this ln v was a function which was going from the subset of E times A, the subset of state actions. Now it is an operator which is acting on some function V, which are function on the state space, but now it is a function from E into R. And the last operator is the maximal reward operator. It is the supremum over all these ln vxa. And okay, so let me see you how this operator is appearing now, because I didn't finish. So I have what I establish here is that Vnx is smaller than the okay, here it is, when I write that, it is a supreme here, f in Fn, okay? So Vnx is less than the supremum over f in Fn of Tn Fn or Tnf Vn plus 1 of x. And this guy is what we call the maximal operator. Yes, so you see, because here it depends only, it is a f in Fn, so it is the same. I think it is the same as the soup over A in Dn x of Tn A Vn plus 1 x. And so this is the operator which appears here. It is a supremum over all the action and ln vxa. And so what we have proved until now is that with this notation, we have proved that Vn is less or equal to Tn of Vn plus 1. Okay, it is what we have proved one inequality, but now we want to prove the equality. So now for the equality, it is a bit more subtle, and it is not, we will have to make some assumptions, but for the moment I write it without any assumption. Assume that there exists a maximal strategy at for Vn plus 1. So what I mean by maximal strategy, it means that Vn plus 1 is equal to Vn plus 1 pi star for some pi star, which is equal to, of course, Fn plus 1 star, Fn minus 1 star. So I assume that this strategy exists. And you see, it is a strategy which has to exist. In fact, this strategy depends on the point x. Here, Fn plus 1 star, Fn minus 1 star are some function of the state x in E. And so we assume that this strategy exists and come back to try to prove the reverse inequality for Vnx. Vnx is a supreme over pi. Okay, now the pi are the supreme over f, all the strategy Fn until f capital N minus 1 of Vn Fn f capital N minus 1 x. And so now, since it is a supremum over all the strategy, in particular, it is bigger than the sup over Fn plus 1 star, Fn minus 1 star. So I use the strategy that I obtained from time n plus 1 to capital N minus 1, and I will just optimize on the first action at time n of Vn Fn, which is to determine Fn plus 1 star, Fn minus 1 star of x. And if you do that, now I use again this property, which is written here, which was the relation between this Vn and this Vn plus 1 pi. So I recall you that here the pi here, which is here, it is the restriction of the pi, which is here, but so 1 second, I have to come back. Yeah, it is here. So you see, there is this here the pi, which is here, is not in fact the same pi as here. It is some abuse of notation because the pi, which is here, is a strategy for time n plus 1 until capital N minus 1, while here it is a strategy from n plus 1, n plus 2 until capital N minus 1. So in particular, if I use this relation which is written here, I can say that it is the supremum over Fn. In fact, it is only the supremum over Fn because now Fn plus 1 star, Fn minus 1 star are fixed, in fact, of R n x Fn x plus the integral over E Vn plus 1 Fn plus 1 star Fn minus 1 star of y Qn y given x fnx. But now, since in fact I have this equality, which is here, in fact I can replace this guy. Exactly, it is equal to Vn plus 1. Why? It is a maximal, the max over all the strategy. And so I come back to the fact that it is a supremum over Fn of Rnx Fnx plus integral over E of Vn plus 1. Y, Q and Y, given that X Fnx. So it is the same. It is exactly with the notation that introduced before. It is exactly the Tn Vn plus 1 of X. And so it is the opposite direction. It is a maximal operator applied to the value at time n plus 1 evaluated at X. So I obtain the reverse inequality. And so I have that Vn at the end. Vn is equal to Tn of Vn plus 1. So, however, when I did that, I was using some assumption. I was using that there exists a maximal strategy for Vn plus 1. And that is not trivial, and that maybe it doesn't exist. So in fact, all the proof is correct, but in fact, I have to introduce in my assumption something which justifies that I have a maximal strategy, that at each step I can find some maximal strategy, some optimal strategy. Moreover, I have to be careful, okay, also about something before to stop. Now, it establish more or less this Bellman equation here. So it was the initial point, and then we established that, but we have to make some assumption about the existence of some optimal strategy at each time. Okay, it is not some global strategy, but at each time when we are trying to maximize this maximal reward operator, we have to assume that there exists some optimal strategy. So there are conditions under which we can prove that there is optimal strategy, but you cannot formulate some general theorem without this assumption. And then you can check in the depending model, some models, if it is true or not. So it will be the reason for which later, next time, I will introduce a real theorem. This is in a nutshell, it is a Bellman equation, but in order that this Bellman equation is satisfied, you have to assume the existence of this optimal, strategy at each time. And so you have to be careful because, okay, there is some problem of measurability. In the spaces are finite. There is no problems. Everything is completely okay, and events existent of the optimal strategy is always true. But it can happen that even if you start with some function v which is measurable, so it is a notation, it is the set of measurable function on E, then it can happen. It can happen that this TNF. Yes, no, okay, it's not, that is no, it is not what I want to say. It is remark one, which is important, is that even if TNF is always a measurable function, it can happen if you have some sets which are infinite, that Tn, the maximal operator applied to a measurable function, is not a measurable function. And so then you will get in trouble. So it's the reason for which we will have to impose some conditions in order to have the existence of some optimal strategy, so that in fact we will work always with these kind of operators, which are good operators in the sense that they are transforming some measurable function into some measurable function. While phys1, apparently, the maximal operator is something which could produce some non-measurable function, and we don't want to work with non-measurable function. Okay, so more or less I prove these equalities, this Bellman equation, but next time I will present the correct setting in which you can prove it correctly, because here I did this assumption. So now I think it is okay. I didn't mix the time, and so I will come back to this optimization problem next time, and we'll make some exercise and some application to see how it works in practice. I don't know if you have some questions or some comments, or if something was not very clear.
Yeah, I think that it was accessible, yeah, but just again, I need some time to put it together in my mind.
Yes, of course. But then it is afterwards we will use this Bellman equation for different models all time, so it will finish to be something much more usual. But yes, it will take some time. I agree. Okay. So I will send you everything by email, this material, this new material, new exercises, and so on. Okay, maybe I don't know, today or tomorrow, I don't know. And next week we will see us only for only Friday. Okay, so it will be less material in 1 week. Okay. If you don't have any other comments or other questions, we'll stop now.
Okay. Thank you.